The 1999 National Electrical Code, or NEC, does not have a specific regulation solely focused on the length of a wire. However, it's crucial to understand how wire length relates to voltage drop in electrical circuits. Annex D within the NEC provides informational guidance on voltage drop considerations. Annex D recommends that the voltage drop on a branch circuit should not exceed 5% of the nominal voltage at the load. This 5% recommendation is not a mandatory requirement but a guideline for efficient circuit design. For example, if you have a 120-volt circuit, the maximum recommended voltage drop would be 6 volts, which is 5% of 120 volts. If the circuit is 240 volts, then the maximum recommended voltage drop would be 12 volts, or 5% of 240 volts. The significance of wire length lies in its direct correlation to voltage drop. As the length of a wire increases, so does its resistance. This increased resistance leads to a greater voltage drop along the wire. Voltage drop is the decrease in voltage that occurs as electricity flows through the conductors of an electrical circuit. This drop is due to the resistance of the wires and the current flowing through them. Excessive voltage drop can cause various problems, including reduced performance of electrical equipment, overheating of wires, and inefficient energy use. Therefore, it's essential to consider wire length when designing and installing electrical circuits to ensure that voltage drop remains within acceptable limits. Several factors influence the voltage drop in a wire, including the wire's length, cross-sectional area, material, and the amount of current flowing through it. Firstly, the longer the wire, the greater the resistance and the greater the voltage drop. Secondly, the smaller the cross-sectional area of the wire, the higher the resistance and the greater the voltage drop. This means a smaller gauge wire will have more voltage drop than a larger gauge wire for the same length and current. Thirdly, different materials have different resistivity. Copper and aluminum are commonly used in electrical wiring due to their low resistivity. Copper generally has lower resistance than aluminum for the same size wire. Fourthly, the higher the current flowing through the wire, the greater the voltage drop. Higher amperage loads will cause more voltage drop than lower amperage loads. To determine if the wire length is a concern, you can use a voltage drop calculator. These calculators are readily available online and in electrical engineering software. They take into account the factors mentioned earlier, such as wire length, gauge, material, current, and voltage, to compute the voltage drop in a circuit. By inputting the relevant parameters, you can assess whether the voltage drop falls within the recommended 5% limit specified in NEC Annex D. If the calculated voltage drop exceeds this limit, you may need to increase the wire gauge, shorten the wire length, or take other measures to mitigate the voltage drop. The formula for calculating voltage drop is as follows: voltage drop equals current multiplied by resistance. Where voltage drop is measured in volts, current is measured in amps, and resistance is measured in ohms. The resistance of a conductor can be calculated using the formula resistance equals resistivity multiplied by length divided by area. Where resistance is measured in ohms, resistivity is a property of the conductor material, length is the length of the conductor in feet, and area is the cross-sectional area of the conductor in circular mils. It is important to use consistent units when performing these calculations. For example, if the length is in feet, the area should be in circular mils. The NEC provides tables of conductor properties that can be used to find the resistivity and area of different conductors. These tables are typically found in Chapter 9 of the NEC. To use a voltage drop calculator effectively, follow these steps. Firstly, determine the circuit's parameters, including the voltage, current, wire gauge, wire type, and wire length. Secondly, input these parameters into the voltage drop calculator. Thirdly, review the calculated voltage drop and compare it to the recommended limit. Fourthly, if the voltage drop is too high, adjust the parameters, such as increasing the wire gauge or shortening the wire length, and recalculate the voltage drop until it falls within the acceptable range. There are several strategies to mitigate excessive voltage drop. Firstly, increase the wire gauge. Using a larger wire gauge reduces the wire's resistance, thereby lowering the voltage drop. Select a wire size that is appropriate for the load and the length of the circuit. Secondly, shorten the wire line. Reducing the wire length directly reduces the total resistance of the circuit and thus the voltage drop. If possible, relocate the power source closer to the load to minimize the wire length. Thirdly, use a higher voltage. Increasing the voltage of the circuit reduces the current required to deliver the same amount of power, which in turn reduces the voltage drop. However, this may require different equipment and wiring methods. Fourthly, use multiple parallel conductors. Using multiple conductors in parallel effectively increases the cross-sectional area of the wire, reducing the resistance and voltage drop. This is more common for larger services and feeders. Keep in mind that the NEC has tables that show the allowable ampacities of different sizes of conductors. For example, NEC Table 310.15b16 provides ampacity ratings for conductors based on their insulation type and installation conditions. It is important to select a conductor size that is large enough to carry the load current without exceeding its ampacity rating. In addition to voltage drop, it is also important to consider other factors when selecting wire size, such as ampacity, insulation type, and environmental conditions. The NEC provides guidance on these factors in various articles and tables. For example, NEC Article 310 covers conductors for general wiring, and NEC Article 400 covers flexible cords and cables. When dealing with voltage drop, it's important to differentiate between branch circuits and feeder circuits. Branch circuits are the circuits that extend from the final overcurrent device to the outlets, while feeder circuits are the circuits that supply power from the service equipment to one or more branch circuits. Voltage drop is more critical in branch circuits because it directly affects the performance of the equipment connected to the outlets. In feeder circuits, voltage drop can affect the overall efficiency of the electrical system, but it is less likely to cause immediate problems with individual pieces of equipment. In summary, while the 1999 NEC doesn't have explicit rules on wire length, it highlights voltage drop in Annex D. Keep wire lengths as short as possible, especially in branch circuits. Use voltage drop calculators to check your work, and don't hesitate to upsize wires when necessary to stay within the recommended 5% voltage drop limit. Always comply with the NEC and local electrical codes to ensure safety and proper performance. Proper wiring practices not only enhance the lifespan of electrical equipment, but also maintain energy efficiency. Remember that electrical work should only be performed by qualified professionals who are familiar with the NEC and local electrical codes. If you are not qualified to perform electrical work, consult a licensed electrician. Doing so helps to prevent electrical hazards and ensures that the electrical system is installed safely and correctly. Lastly, it is important to remember that the NEC is a minimum standard, and good engineering practice may require exceeding the requirements of the NEC in some cases. For example, it may be desirable to limit voltage drop to less than 5% in certain applications where voltage-sensitive equipment is used. By paying close attention to these details, you can design and install electrical circuits that are safe, efficient, and reliable.